Okay, so section 8.6 deals with representations of functions as power series. So you've learned a lot about power series. You learned a lot about them. Yesterday we talked about power series, and you had some homework on power series. And so basically in yesterday's assignment, what your goal was to look at these power series and determine what the interval of convergence is. And of course, if you know the interval of convergence, then you know the radius of convergence. And it's very important to understand how to find interval of convergence, because we're ultimately concerned about taking these power series, taking functions and expressing them as power series. So but for a like here, you say, like, you have this function f of x is equal to 1 over 1 plus x squared, and we want to express we want to express this rational function, which, as you know, sometimes they're difficult to deal with, rational functions. We want to express the rational function as a power series. But the function will only equal its power series for x values where the power series converges, or for the interval of convergence for the power series. So this is why it's important to be able to identify interval of convergence. In section 8.6, we're adding the task where we're given the function, write the function as a power series, and then find the interval of convergence. Okay, so all right, let me give you a moment to copy that down. Okay. Okay. So we want to find the power series and interval of convergence for this function f of x equals 1 over 1 plus x squared. All right. Now what I'm going to do is I'm going to do something that you haven't done in a long time. Division by hand. Before we get to this problem, I'm going to do a little aside here and remind you what division by hand looks like. So let's say, for instance, that you wanted to divide 2,475 by 5. Okay, how would you do that? All right, well, how many remember doing this maybe in elementary school? What you're seeing here on the board here, this kind of division. Okay, Josiah remembers it. Okay, thank you. All right, Robin, Ryan, Tyreek remember, Julia, great. So of course what you do is you put 2,475 here inside the box, and you divide by 5. 5 goes into 24 4 times. 4 times 5 is 20. You subtract, you get a remainder of 47. 5 goes into 47 9 times. 9 times 5 is 45. You subtract, you get a remainder of 25. And then 5 goes into 25 5 times, and so you get 495. So therefore, 2,475 divided by 5 is equal to 495. Well, we can do something similar. We can do something similar for our situation here when we take 1 divided by 1 plus x squared. I want to divide 1 by 1 plus x squared. So I'm going to set the problem up just like, well, hold on here. I want to be a little bit careful. What I'm not going to get there just yet. But I want to say this the right way. The key is this process here of division. This process of division, it's important that you, I mean, I know now, like, you use calculators to do division, but this process where you learned how to divide a number by another number, and the process here in the circle process is important. So what I want to do next is I want to take 1 and divide it by 1 minus x. Okay, I want to now advance myself from dividing a number by number to dividing a number by a linear expression. So when I take 1 and divide it by 1 minus x, I'm going to do the same process that I did here. So 1. So let me show you on the next page. So let's divide 1 by 1 minus x. Okay, so here's the 1 right here. Right? Divided by 1 minus x. So 1 goes into 1 minus x 1 time. Okay. 1 times 1 minus x is 1 minus x. And when you subtract that, 1 minus the 1 minus x is an x. So it's just like you're doing regular division. It's just you're doing it with a number divided by a linear expression. 1 over 1 minus x, the remainder is x. That's the remainder. So how many times does 1 minus x go into x? It goes in x times. So x times 1 minus x is x minus x squared. And then you subtract the x minus x squared from x. You know, the x's cancel out, and you're left with x squared. Right? Just like the 1's canceled out here. All right, and now x squared times 1 minus x is x squared minus x cubed. All right, and you keep going. All right, well, 1 minus x goes into x squared times. And so basically, you're able to show that 1 over 1 minus x is equal to 1 plus x squared plus x cubed, and that equals the sum, where n equals 0 to infinity, of x to the nth power. So are there any questions on this? Are there any questions on this process here? How many recall doing this process, incidentally, maybe in pre-calculus? You might have seen this in pre-calculus. I mean, I think you would have, but how many recall doing this kind of thing? Taking polynomials and dividing by polynomials. Yes, Tyreek's seen it. So you all, how many saw it but kind of didn't like it? How many remember seeing it but didn't like it? All right, well, you liked it, so good. Okay, so what we've done then is, and we can see, you know, that 1 over 1 minus 1 divided by 1 minus x is 1 plus x squared plus, and we know the next term will be x cubed, and the next term, you know, will be x to the 4th, and so forth. We can see the pattern here. We can see the pattern. So 1 over 1 minus x is equal to 1 plus x plus x plus x squared plus x cubed, which is the series n equals 0 to infinity of x to the nth power. That's a power series. But also, what kind of power series is this? 1 over 1 minus x equals a special kind of power series. Look at the series. What kind of special power series is that? The power series behaves like a what kind of series? Geometric series. Good, Robin. That's right. So okay. Well, whenever we talk about a geometric series, we think about common ratio. What's the common ratio here? What's the common ratio? That's right. Good, Robin. Good, John. X. So this function, 1 over 1 minus x, will equal that power series, but only where the power series converges. And we know that this power series, which is a geometric series, converges when when the absolute value of the common ratio x is less than 1, or when -1 is less than x, which is less than 1. Okay. Are there any questions so far? Okay. So let me ask you, if we had 1 over 1 minus a half, would that be equal to that power series? Is 1 over 1 minus a half, and we know 1 over 1 minus a half is 1 over a half, which is, well, I want to be careful. Let me be careful. 1 over 1 minus a half, can we say that equals the series where n equals 0 to infinity of 1/2 to the nth power? Can we say that? Is that true? What I'm doing is I'm picking a value for x. I'm saying let x be a half. I'm saying let x be a half. Right? Here I'm saying let x equal a half. And then 1 over 1 minus a half, would that equal then the series, this series here, where n equals 0 to infinity of 1/2 to the nth power? Should it be equal based on your interval of convergence? Yes, Robin, it should. It should be equal because 1/2 falls within your interval of convergence. The interval of convergence is x is between -1 and 1. Well, 1/2 falls in that range. What will this series equal? What will this series equal? I mean, the terms of the series are going to be what? 1 plus 1/2 plus 1/4 plus 1/8 and so forth. What will that series equal? Okay. Well, let me ask you this, and Robin and everybody. We agree that this series here. Hold on. Let me maybe make it in purple. We agree that this series is equal to 1 over 1 minus 1/2. Well, what is 1 over 1 minus 1/2 equal to? 2. That's right. That's right, Robin. So this series, it's not a power series anymore because we've put a value of x in it. We're saying let x be 2, or x be 1/2. The series itself will equal 2. Okay? All right, are there any questions on that? Please stop me if you're uncomfortable. You have to stop me. What I'm trying to do is make this idea of a function equaling, if a function's going to equal a power series, then when you put in a value of x into the function, the power series, when you put in the value of x into the power series, you should get the same answer. Right? Well, that's only going to be true for when your values of x are in your interval of convergence. Okay. Now let's look at another value. Let's say you had 1 over 1 minus 3. If we follow the formula for the power series, 1 over 1 minus 3 will be the sum starting at n equals 0 to infinity of 3 to the nth power. You tell me, well, so 1 over 1 minus 3, 1 over 1 minus 3 equals -1/2, right? So is 1 over 1 minus 3 equal to the series where n goes from 0 to infinity of 3 to the nth power? Does 1 over 1 minus 3 equal that power series? Not power series. Does 1 over 1 minus 3 equal that series? Is that sum on the right, the sum where n equals 0 to infinity of 3 to the nth power, equal 1 over 1 minus 3? Josiah doesn't think so. Why not, Josiah? What can you tell me about this series, n equals 0 to infinity, 3 to the nth power? It diverges. Excellent. It diverges. So these are not equal. Those are not equal. And it makes sense because the power series, its interval of convergence is between -1 and 1. But 3 falls outside that interval of convergence. You see what I'm saying? So you can't say the series when x equals 3 equals the function when x equals 3. You can't use the series representation of the function. You can't use the series representation of the function for x equals 3 because you get this nonsense, you know, and that's because x equals 3 falls outside your interval of convergence. The interval of convergence is x is between -1 and 1. X equals 3 falls outside that interval of convergence. Okay, is this helpful? Is this helpful, this little discussion? Thank you, Robin. Anybody else? Okay, great. Okay, wonderful, wonderful. All right, all right. Thank you, everybody. Thank you. So remember, our original goal was to find power series and interval convergence for this function, f of x equals 1 over 1 plus x squared. Well, we've established right now, that we've established this rule here, that 1 over 1 minus x is equal to the geometric power series n equals 0 to infinity x to the nth power when x is between -1 and 1. So what I want to do, since my function is 1 over 1 plus x squared, I want to make use of this result. I want to make use of it. Okay. It took us a little while to get this result, but we can make use of it. So, like for instance, let's say, and this is sort of a Dr. Duty special here. What if I had 1 over 1 minus an apple? Okay, so I don't have 1 over 1 minus x. I have 1 over 1 minus an apple. If I apply the formula above, if I apply this formula, 1 over 1 minus an apple would equal the series n equals 0 to infinity of apple to the nth power, where your rule of convergence is that the absolute value of the apple is less than 1, or that the apple is less than 1 and greater than -1. All right, so does my transition from the first formula to the second formula make sense? There's a reason I'm doing this, but can you accept it? Very good participation today in class, by the way. Very good participation. Can you? I mean, how many of you are saying, "Well, this is kind of crazy, but I'll accept it. I'll accept this second formula here, based on the first formula." All right. Good. Good. Thank you, Julia, John, and Robin. Okay. Thank you, Tyreek. Wonderful, wonderful. So, okay, why would we want to do this? Why would we want to do this? Well, let's go ahead now and get to our example where we have the function equal to 1 over 1 plus x squared. May I move to the next page? Are we comfortable here? Are there any questions? Okay. So what we're going to do is we're going to take this function 1 over 1 plus x squared, and we're going to express it so that we can use the Apple formula here. I want to use the Apple formula. Well, to use the Apple formula, I have to have a minus. In the denominator, I have to have a 1 minus an apple. 1 minus an apple in the denominator. I already have a 1 in the numerator. So I need a 1 minus apple in the denominator. So I rewrite 1 plus x squared as 1 minus negative x squared. And the negative x squared here will serve as my apple. So I have 1 over 1 minus my apple. That's going to equal the power series, where n equals 0 to infinity, of my apple let me put that below, to the nth power. Right? All we did was apply the Apple formula. And we note that the absolute value, remember, of the apple had to be less than 1, right? The absolute value of the apple had to be less than 1 for the interval of convergence. So that means the absolute value of negative x squared is less than 1. But negative x squared's, the absolute value of negative x squared is positive x squared. So x squared is less than 1. So x is between negative 1 and 1. So you've taken this function now, and you've expressed it as a power series and you've identified the interval of convergence. All right, are there any questions so far? All right, well, but this formula, this power series, can be written in a more beautiful way. We don't want to leave the power series written in this form, and there are reasons for this. We want to simplify it a little bit. So we recognize that negative x squared is the same as negative 1 times x squared. And then we're taking that product and raising it to the nth power. That's the same then as having negative 1 to the nth power times x squared to the nth power. Okay, are there any questions so far? All right, well, then negative 1 to the nth power just stays negative 1 to the nth power, but x squared to the nth power, that's x squared raised to the nth power. We multiply the exponents to get to the 2nth power. Okay, and so this is going to be your power series right there. So your power series is n equals 0 to infinity of negative 1 to the nth times x to the 2nth power, but I've written out just some terms of the power series. So this is a big moment for you. You've taken your first function and you've expressed that function as a power series. Okay, it's kind of like, how many remember when you got your driver's license? That moment that the DMV gave you your driver's license. You know, that's right. Josiah knows what I'm talking about. John and Tyreek knows. Yeah, you feel like, wow, you know, I'm like a new person. You know, I have this ability now. new ability. Well, same thing here. So this means then, in summary, this means that for when x is between -1 and 1, this rational function 1 plus x squared can be expressed as this power series. Okay. And you might wonder, well, you know, why is this? How could this be used? You know, why would we be interested in that? Well, let's say, for instance, that you wanted to integrate 1 over 1 plus x squared you wanted to integrate that function. Okay, so we're looking at the integral from 0 to 0.5 of 1 over 1 plus x squared dx. Incidentally, can we, and this is just an aside, we've done the problem, but can we get the exact value of that integral? Is there an antiderivative of 1 over 1 plus x squared? What is the antiderivative of 1 over 1 plus x squared? I think you know it. That's right, Robin, the arctangent. So very good. So we could find the exact value, but we could also, I mean, let's say that we had a function here that we couldn't get the antiderivative of. Let's just say. What we could do is we could integrate the power series. See, we could integrate the power series. It's -1 to the nth x to the 2nth dx. Right? So if you have a integral where you can't find an antiderivative, this one you can, but yet you need to find a value for the definite integral, you can actually approximate that value by integrating the series for that function. But of course, your limits, which are 0 and 0.5 in this case, have to fall within the interval of convergence in order to do this. And I'm going to show you that. We might get to this today. We might get to it tomorrow. But how many think that idea is kind of cool? How many think that's kind of an interesting idea? Absolutely, absolutely. And that's right. Thank you, John. Thank you, Josiah. It's very cool. Tyreek likes it. Sachi likes it. Okay, great. So this is, you know, this is a preview of what's coming up. Really, really cool stuff. Okay. Well, let us proceed on here. Let's look at another problem. We want to find the power series interval of convergence for this function here, f of x equals x cubed over x plus 2. Let me give you a moment to copy that down. Okay, so again, here we have another rational function, x cubed over x plus 2. And what we want to do is we want to manipulate this rational function so that we can get it, so that we can use our Apple formula. Okay, it worked before for the first example we did. Let's see if it works for this example. So again, what we need here for the Apple formula? Well, we need a 1 in the numerator, and we need a 1 minus an apple in the denominator. Okay, we need a 1 in the numerator and a 1 minus an apple in the denominator. So what we can do here is I can write this function as x cubed times 1 over 1, x cubed times 1 over x plus 2. Okay, I mean, by doing that, I have a 1 over x plus 2 here. So ideally, of course, you can imagine what we're going to do. We're going to replace the 1 over x plus 2. We're going to try to find a power series representation for that rational function. And then we'll have x cubed times that power series, and then we can bring x cubed inside the power series later. But that's what we're going to do. Now, the formula is 1 that we have is 1 over 1 minus an apple, right? That's what's on the left side of the formula. So I have 1 over x plus 2. I have the variable first here. I'd like the number first. So I'll write that as 1 over 2 plus x. So now I have 1 over 2 plus x, but I have a 2 here, right? I have a 2. What do we want there? What number do we want there instead of the 2 for the Apple formula? That's right, Robin. We want a 1 there. Okay, well, what I'll do then is I'll factor a 2 out from both the 2 and the x. I mean, we can do that. We don't normally do that, but we're going to do it here. I mean, sure. 2 times 1 plus x over 2 is equal, if we distribute the 2, that equals 2 plus x. So now I got the 1 where I want it to be. I got the 1 there. And I can write this as now x cubed over 2 times 1 over 1 plus x2, plus x over 2. So the fraction is looking better. Looking better. But what do we want there instead of the plus? Instead of the plus, what do we want there? Well, are there any questions so far? All right, so we have a 1 plus x over 2 in the denominator, but we don't want a plus there. We want a minus there. So, okay, all right, 1 over 1 plus x over 2 as 1 minus negative x over 2. We can do that. And so now you're ready to apply the Apple formula. Negative x over 2 is my Apple. Okay, so I can rewrite my rational function as this power series, n equals 0 to infinity of negative x over 2 to the nth power, which is the Apple to the nth power. But we note that the absolute value of my Apple, the absolute value of negative x over 2 is restricted. It has to be less than 1, right? Well, that means the absolute value of x is less than 2, and x is between negative 2 and 2. Are there any questions so far? Very good question, Robin. I was actually ready to discuss that. Robin asks, are we required to manually check the endpoints? The answer for section 8.6 problems is no. The answer is no. So in section 8.5, when you were looking at power series problems, you you had to test the endpoints. You would get an interval of convergence, but then you had to test the endpoints. But you don't have to do that for the problems from section 8.6. Why is that? Why is that? Well, let's go back and look at the formula. Let's go back to our Apple formula. Okay, when we came up with our Apple formula here, 1 over 1 minus an Apple would equal the series n equals 0 to infinity of Apple to the nth, where the absolute value of Apple is less than 1, or that's the same as saying that the Apple is less than 1 and greater than negative 1. So, okay, we didn't worry about testing the endpoints here when we came up with our Apple formula. Why didn't we worry about testing the endpoints? Why didn't we have to worry about that? Who thinks they can offer a reason? And remember, the Apple formula was based off of this formula here that we derived. The 1 over 1 minus x formula. Why didn't we have to worry about, well, let me ask you this. Let me make it a little easier. Let's start at the 1 over 1 minus x formula. So 1 over 1 minus x equals the power series from n equals 0 to infinity, x to the nth power, where x is between -1 and 1. That's your interval of convergence. Why didn't we have to test the endpoints -1 and 1 there for that formula? Why didn't we have to? What special series did we obtain for when we divided 1 over 1 minus x? What special power series did we obtain? Did we get? That's right, Robin, a geometric power series. Very good. So we got a geometric power series, and the common ratio was the absolute value of x. And we know for a geometric power series, the interval of convergence, you know, geometric series converge when the absolute value of the common ratio is less than 1. That's it. There's no other x, nothing else to consider. So for our power series, the common ratio was x, so the absolute value of x is less than 1. That means the interval of convergence is x is between -1 and 1. Well, for our Apple formula here, the Apple formula came about based off of the 1 over 1 minus x formula. And so the interval of convergence for the Apple formula is Apple is between -1 and 1, and we don't need to worry about testing the endpoints. So anytime I use this Apple formula, I don't need to worry about the endpoints. And all the problems in section 8.6 are based off of this Apple formula here, which is why you don't need to worry about testing the endpoints. Okay, and therefore, for this particular problem, we can say the interval of convergence is between -2 and 2, and we don't need to check any further. All right, and you know, if you were, let's say you were to put in x equals 2, just out of curiosity, if you were to put in x equals 2, the power series, right, I won't put n equals 0 to infinity. If you were to put x equals 2, you'd have -2. I'm talking about plugging in x equals 2 here for x. You'd have -2 over 2 to the nth power. We won't worry about the x cubed over 2 yet. That's the same as the series where you have -1 to the nth power. And all that series is going to do is it's going to be, if you expanded that series out, you'd have, you know, 1, -1, +1, -1, +1, -1. The series wouldn't converge. So I mean, you can if you want to mentally put in the endpoint values into the series, you can see for yourself that you know, that this is the interval of convergence. All right, does that help? Did that help, Robin? Are you feeling a little more comfortable now with that? Great, and hopefully everybody is. So okay. So here we are. We have this for our function, our original function was what? It was x cubed over x plus 2. We have this power series, but we want to simplify that. Okay, we're going to simplify that. So I rewrite this. Here's what we had. We had x cubed over 2 times the power series. I rewrite the power series in a nicer way. Okay, I rewrite the power series in a nicer way. Are there any questions up to that step there, where I've check marked that step? And this kind of work I'll be looking for on your next exam. Okay. Again, showing the work's very important. A few of you, well, actually, some of you missed some points on a couple of the, what was it? The, oh, forgive me, I have to think here. Separation of variables problems, where you had integrals where you needed to do integration by parts, and you didn't show the integration by parts step. You may have gotten the right, you've got the right antiderivative, but you can't get that antiderivative for that part of the problem without without doing integration by parts. So you always have to show work. You always have to show work on your steps. Okay, I want to see more than what you might see in a textbook solution. So you want to show this work. Okay, it's easy to show. No reason to miss points on a problem, right? I'm testing you for understanding of the concepts. So I need you to show me that you understand all the concepts. Okay, well now x cubed over 2. All right, this series, we have a power series times x cubed over 2. Can I take the x cubed over 2 and bring it inside the series? Is it okay to do this? To bring the x cubed over 2 inside the series? That's right, John. It is fine, because x cubed over 2 is not dependent on n. It's not dependent on n. So x cubed over 2 relative to the power series is just like a number. It's like a constant. Okay, so we can bring x cubed over 2 inside the series. So now sometimes students have a little trouble seeing that, but look, you could think of it like this. If you were to go from this last step to the step before, x cubed over 2, could you factor that out in front of the series? Sure, you would have no problem doing that, because x cubed over 2, that expression isn't dependent on n. So, well, similarly, then, if x cubed over 2 is out in front of the power series, you can bring it inside the power series. And the reason we do that is because then we can make the series look a little nicer. We can make the series look a little nicer. We can x cubed times x to the n is x to the n plus 3. And 2 times 2 to the nth is 2 to the n plus first power. And so it makes the series look nicer. So this is what I want to see when you do these problems. Okay, let me pause for a minute and see if there are any questions. Okay, so let me just add this here. So x cubed over x plus 2 that rational function is equal to this power series, but only for x values between -2 and 2. Only for those x values. Are there any questions on that? Okay, so one thing I'll mention here, so like WebAssign would probably, let me just clear this board here a little bit. Like in WebAssign would probably accept this answer. If you had to type in, you know, like manually type in like this part here, WebAssign would probably take that answer. But for your next exam, I'm going to want this as your answer. Because this answer here, I'll put a little smiley face here. I don't know, is that a good smiley face? I don't know. This answer here, I'll make that better there. This answer here is in like the most simplified form possible, and that's the form I'll want to see in your work. Okay, so to get full credit for a Section 8.6 question on an exam, I would want to see your answer fully simplified. Okay. All right. How many feel better just having the answer fully simplified? Who gives it? Who wants to give a thumbs up on that? Do we have any? Okay, I was hoping I might see 5 thumbs ups, 5 thumbs ups right away, but all right, no, I got to have at least one. All right, thank you, John. I'll sleep better knowing one person at least is. You're gonna. I mean, you're gonna understand also the value of having the series in this simplified form. I am a little choosy on work and answers, but it's because I have high expectations of you. It's because I care. I know that being thorough and getting answers simplified and showing work, I know that is going to help you in your future, right? I know that's going to help you with your future math, you know, ultimately it's because I care. All right, let me stop the recording for a moment,